Good morning, everybody, and welcome to my session for today. My name's Sophie Parry. I'm your presenter for the next hour. A little bit about myself before we start. I'm a technical applications consultant for Zumtober Group Lighting, which is an Austrian company, a worldwide company, and I basically look after the UK and Ireland in terms of technical consultancy and for both product and applications within the lighting industry. I'm also, outside of my day job, the chair of SIBSE's Technical and Publications Group for the Society of Light and Lighting, which is SIBSE's specialist division just for lighting. So I look after a team of about 18 authors, and we're responsible for all of the technical publication output of the Society of Light and Lighting. So you may be familiar with the lighting guides and the lighting handbook and the code for lighting. That all comes through my team. Anyway, without further ado, I will start today's presentation. This is all about the British standard for light and lighting of indoor workspaces. So it is in various parts, and part one is purely about the indoor workplace. This is where all of the metrics come from for indoor lighting, if you like. It's sort of the source of all of that information. It was last updated in 2011. And then in 2021, we saw further updates and some quite radical changes at a very interesting time in building service history. So let's have a look at where we left off with the 2011 version and what's different in 2021 and how it might impact on lighting projects. So we'll look at the existing use of the 2011 version, how we left off, what it degenerated to for most designers, and then we'll look at the key changes. So really, to summarize these key changes, there's a lot of due regard paid now to the people that actually use the space. So humans being the variable in lighting design, and in particular their eyesight quality or visual acuity. We'll then move on to the scope of indoor applications, just to confirm that they're still there. We won't go through them painfully one by one. And then we'll look at what the key changes are and what they actually mean, including a worked example where context modifiers are used based on the activity in a space and also perhaps the visual acuity of the people using the space. And then at the end, we'll just summarize with 3 takeaways from today's session. So how did we finish up using the existing standard, the 2011 version? Well, you're probably familiar with seeing Dialux plots, for instance. So this was very much a case of what I call lighting by numbers for some people. They would start to do a lighting design in a lighting software program such as Dialux, and they would try various luminaires, and eventually they would find a luminaire that gave them what they wanted in terms of metrics. They got the right lux level, the uniformity, the UGR was there below the magic 19 usually, and all of these numbers seem to line up, and you got that nice little bill of quantities of which luminaire you needed and how many. And as you can see from the drawing, this is a sort of symmetrical arrangement. That's fine, but this is really hitting numbers to satisfy what your customer or client wants, and it doesn't actually take into account the people using the space. It's just about hitting those metrics. So fine, we can hit numbers, and in most cases, we've got a happy customer. We're probably meeting a specification requirement or complying with a standard or the employer's requirements. Job done. But we have to think about the people using the space, which is a big part of the new standard, which never really happened in the 2011 version. And one area that I've done quite a bit of research in over the last few years is the psychology of making decisions of which luminaires to use. So creating a model and saying we found luminaires that hit those magic numbers, and then perhaps presenting 3 or 4 different luminaires to the ultimate client, either as a series of luminaires placed on a table for decision making, or even construction of a mock-up. This is where it gets interesting, because those, you might say, well, there's 4 different luminaires here that could do the job, and you need to make a decision which one you want to go forward with. They all look slightly differently, maybe slightly different price points, but usually the person making the decision is only around for, say, maybe 10 or 20 minutes at the most, and they go, I like that one. And you have to ask yourself, well, why do you like that one? You're not actually going to work under this light. but you are subjecting other people to maybe working under it for maybe up to 8 hours a day in a study space or an office. So let's just stop and think about this, because this could be an emotional decision you're making based on the fact that that luminaire is the brightest and sparkliest one on offer, and your attention has been drawn to it on that basis. But quite often, the brightest and sparkliest luminaire has the worst glare characteristics, which means over time, anybody using the space where this luminaire is going to be installed is probably going to suffer from some sort of eye strain, which is going to impact on productivity or the ability to learn and absorb knowledge. And something else that we'll discuss further on in this presentation, which is now in the 2021 version of the standard, is flicker as well. It's an insidious problem with lighting. We had it with fluorescent lighting, and it crept into LED lighting to a certain extent. But again, it causes eye fatigue over a period of time, which means that during, let's say, an 8-hour day, somebody working in an office is slowly going to lose concentration because their eyes are getting tired. Or if you're studying, again, you're not going to be able to absorb as much information. So hopefully some of the information I'm going to give you in this presentation will also lead to making more informed decisions about the luminaires that are ultimately selected for a project, rather than perhaps just the lowest price. So what is actually covered in 12464 part 1? Well, pretty much the same as the last version. There's a whole series of tables in Appendix 1. And these are the headline applications. So you can see it covers just about every eventuality you may encounter as an application in an indoor space within the working environment. And of course, education is in there as well. And the example I will give later on will be based on a lecture theatre and how you might have to design to this new standard. But in total, there's 52 tables. And again, the table layout has changed. So again, when I show you the worked example, I'll show you the new table layout, and we'll go through the headings to make sure that you're familiar with what they mean, because there are some additional metrics that have now been added. But otherwise, if you're familiar with the standard, the tables are still there. There's just a different layout, and some of the values have changed as well. So what are the key changes that we need to look at? Well, some of them are not new. Some of them are, if you like, been around a while. They've just been brought to the fore in this standard. They're becoming more and more relevant, whereas in the past we knew about them and maybe they're only used in certain situations, or even kicked into the long grass and thought not to be so important. So the first one that's been reinvigorated is the CIE scale of illuminance, and that will become obvious as to what that is and how it's used and why it is the way it is as a scale of illuminance later on in the presentation. Cylindrical illuminance, which we do generally use in education, particularly on student and speaker faces to aid communication. Um, rather than just relying on the verbal word, because with just the spoken word, you would have to listen harder. It's probably a bit like listening now, and the reason my camera's on is so you can see me. Because it's a virtual presentation, at least you can see who's speaking, and there may be some additional communication coming through with facial expression or body language. Another one, which has perhaps been amplified a little bit, is discomfort glare. RUGL basically means UGR, or the limit of the UGR. And again, I'll show you a worked example of that, and where the standard's now taking that in terms of perhaps making sure that you get it right. Required and modified illumination levels, context modifiers. You may have heard some urban myths about these, that we now like waste paper bins to 1,000 lux. That's not true. But it could be true if the standard got into the hands of perhaps somebody who didn't really understand what they were looking at and weren't able to make lateral professional engineering decisions. So the worked example will go through that, and we'll bring that one out and lay it bare, so that there is no urban myths, hopefully, surrounding it after we finish this presentation. The next one is new, temporal lighting artifacts. This is a collective term, and from this collective term for this standard, we now address stroboscopic effects and flicker. So stroboscopic effects by the metric SVM and PST LM for flicker, and I'll explain a little bit more about that and how to check luminaires against those metrics at the specification stage. LENI, Lighting Energy Numeric Indicator. This has been around since 2007, but not often used, although it does appear in the building regulations, for instance. It now appears in this standard, and we'll actually look at the benefits of using a LENI calculation, as opposed to just looking at the watts per square meter on the bottom of a lighting plot, because it can be helpful and save you a lot of time in terms of hitting perhaps energy numbers that you need on the project, or you've been given as an employer's requirement. And then finally, non-visual effects of light, which is a relatively new subject coming into electric lighting. So we'll just talk a little bit about that as well, as it appears in the new standard. So let's start off. So the key driver to these changes is human beings, people who actually want to use the spaces we light. To be honest, as a lighting designer, life would be a lot easier if people didn't actually want to use the spaces we light, but they do, and that's why we light them. And we need to think more and more about the people, particularly in offices where it's fair to say that we do have an aging population, but also some people are born or develop visual impairments very early on in their lives. So, you know, we have to think about visual comfort versus the task performance. We could light things very brightly and say, there, you can see it, get on with it. The task is perfectly lit for you, but there could be a lot of glare associated with that. So we also have to balance that with visual comfort for the individual. I'm not going to do a separate presentation on eyesight, but just to give you an idea, these are some of the things that can affect somebody's eyesight, either from birth or they develop as they perhaps even in childhood, through to middle age and beyond. So if you hear me talking about visual acuity, it's essentially a catch-all term for this, but this would be a separate presentation in itself. But I will say, I'll just dispel a popular myth so you'll understand perhaps where this is coming from, is that we don't really see with our eyes, we see with our brain. The human eye is actually a conduit or a gateway to the brain. So what you've got is reflected light from a surface, which will convey information about color and texture through the human eye, which is essentially a collecting lens, to the back, the retina, where there's a series of cells which convert the light into electrical signals through the optic and then down the optic nerve to the brain, and then the brain actually interprets the signal it's receiving. So obviously, if there's a problem with the eye and you're not getting enough light in to get the right signal to the brain, then you need more light to overcome those losses, which is where it gets interesting. And it's not as simple as just saying, just keep lighting until people can see. But we'll explain a little bit more about that in engineering terms and what the standard says we should do about it. So I mentioned cylindrical illuminance and also modeling ratio, which is very closely allied. But let's talk about cylindrical illuminance. Why is it called cylindrical illuminance? We don't illuminate cylinders normally. Well, the reason we call it cylindrical illuminance, this is all about lighting people's faces, so to aid communication. So if you look at the first principles of the mathematics behind cylindrical illuminance, they are actually based on using the surface of a cylinder to develop calculations, and the cylinder represents the human head and more to the point, the face. So as you can see in that green band there, we have two medium-sized adults, one sat, one stood, but both their heads appear in that green band. And that's where we need to think about cylindrical illuminance or vertical light falling on their faces. And the reason we want to do that is that when somebody's talking or teaching or presenting, it's really good if the other person or the audience or the students can see that person's face, because just speaking is a fair part of communication, but also facial expressions and body language also are an important aspect of communication as well. So if you can't see the speaker very well or at all, then it becomes harder for information exchange to take place. So I'm using my camera at the moment. I can't see myself on camera, but I believe you guys can see me. So at the moment, I am if you like, I'm forward lighting a wall in front of me on the opposite side of my computer, which is reflecting some light quite evenly on my face. So you should be able to see me quite well. But for instance, if I was to switch that light off, you'll probably see now that one side of my face has gone very dark and shadowy. Now that may look very dramatic if we were making a horror movie or something like that. But in terms of me speaking to you, either perhaps trying to teach you something or in a meeting where important information had to be conveyed, that poor quality lighting that you now see would be of no help at all, which is why we have to concentrate on delivering cylindrical illuminance. So what it is basically, the modeling ratio, which is allied to this, if we look at that desktop there where we've got the orange circle on, what we call the task area, that's illuminated to 500 lux. So the cylindrical illuminance in the green band, if you like, a vertical line in front of each person's face, should be within 0.3 to 0.6 of that task area illuminance as a lux value for it to be effective. And actually the new table layout I'm going to show you for many applications, and particularly education, does actually have a minimum cylindrical illuminance value that you should achieve on a project to comply with the standard. So the next one is discomfort glare. You've probably heard of UGR, Unified Glare Rating. Our UGL caused a little bit of confusion at first when people first opened this standard from September last year. Our UGL is is a similar metric to UGR. It just means it's the maximum limit of UGR you can go up to, and you shouldn't go beyond that for a particular application. And of course, you'll find the our UGL or UGR value in the tables that I told you about, and you will see that in the example later on in this presentation. So one thing I would like to say about this, because you need to think about glare or discomfort glare in anywhere where people spend any length of time, from a reception desk to a lecture theatre to an office, for instance. Discomfort glare will creep up on people. It will affect morale and productivity if you've got lighting with glare. So most people will look at a data sheet and say, this data sheet says this luminaire is UGR 19 or less. That's okay. This is the one we're going to use because the data sheet says UGR 19 or less, and the employer's requirements say the luminaire should be UGR 19 or less. Well, it's actually not as easy as that. That is not an absolute number. It's a relative number from when the luminaire was tested in a photometry laboratory, usually at the manufacturer's factory, at a certain height above floor, the measurement would be made, and also the spacing with other luminaires in a larger area where perhaps there's 3 or 4 rows in a large room. So it's very much based on the metrics at the time of test in a laboratory and not your project. So you need to go a little bit further. That UGR 19 or less on the data sheet puts you in the ballpark, but it's not the full story. And also, not all luminaires need to be subject to UGR considerations. It's usually only luminaires which have a downward facing light source when they're installed, which is most luminaires. But then there are other variations of luminaires, such as wall washers. They don't need to be included in UGR considerations. Indirect lighting, so if you've got up lighting, for instance, and you're bouncing the light off the walls and the ceiling, that doesn't need a UGR consideration. And also asymmetric or double asymmetric lighting, where the light actually comes out of the luminaire sideways. So you may have a corridor or even part of a lecture theatre where you've got a long luminaire, a long linear luminaire, but the light's coming out sideways to light an information wall, for instance. And of course, adjustable spotlights, because it's a bit like an MOT on a car. It's only as good as the day you do the calculation, because they are adjustable and people will move them around, which means your calculation was worthless. So what can we do to make sure that the UGR is where we need it to be on the project? Because glare is a problem. So what you can do in most lighting modeling software, you can do a UGR study. So this is one from Dialux that I've just put up on the right hand side of the screen. So here we have this highly irregular space shape. It's 2,000 square meters of open space, and I've taken the rows of luminaires out of the model just to make it clearer for the purpose of this explanation. But all of those purple circles with the arrows pointing in, those are what we call observer positions or calculation points. So this is where somebody may be in the room, either sitting down or stood up with their back to the wall, looking down the possible furthest length of the room, and therefore across the possible furthest number and rows of luminaires. So this is where they might be subject to the worst case glare in that room if they're unfortunate enough to be sat in that or stood in that position. So when you load this up into a modeling program, the file for the luminaire should also have all the UGR information included in it, and it will allow you to run this test. And it will tell you for your particular project, with your ceiling height on your project and your luminaire spacings, particularly to your project, what the UGR is likely to be. And that's in the table on the far right-hand side. I've put a red box around it to make it clearer. But you'll see this luminaire that was used on this project, the data sheet said luminaire is UGR 19 or less. But if you look at the values, they're actually less than 19. They range from 13 up to 17 and a few points in between, which is quite good. And the reason that study has come out so well from a UGR point of view is because it's a relatively low ceiling in that room. It's round about 2.7 meters. Okay, now if the architect came along and said, do you know what, we're value and engineering on this project, we're not going to have suspended ceilings, we're just going to go for open soffit and exposed surfaces, so your luminaires will need to go on suspension wires, and the soffit's at 4 meters, so you need to be just below the mechanical services with your lighting, and suddenly your lighting goes from 2.7 meters above the floor to perhaps 3.7 meters above the floor. That same luminaire then, although we're getting good values now, is going to give you very different UGR readings if you run this calculation again. And the chances are you could be up around about 20 or 21, which means you've now got a bit of a glary situation potentially on a project. So you need to do something about that at the design stage before it's too late. Otherwise, it's going to be an expensive fix. So what the new standard is recommending is that you don't just look at UGR numbers on data sheets. You also model UGR as part of the design process to make sure you get it right, because the data sheet is not, as I've just explained, is not always going to be right, because it's a relative number, not an absolute. Okay, so required and modified illumination levels, context modifiers. I think it's important that we look at these before we go to the next slide where we look at an example. So what we've got is table 1 and table 2. It's like doing a mini risk assessment. So what you'll see on the application table is you'll have a default lighting value. Um, which could be 300 lux, could be 500 lux for your task area, which you're probably familiar with, that sort of thing. But you have to ask yourself these questions as part of the design process. So, you know, is the work being done in the area critical? Are errors costly to rectify? And then that one at the bottom, the visual capacity of the worker is below normal. Now, these, the wording on these is quite loose, but you either have to ask yourself these questions as part of consultation with the person who's responsible for the use of the space, if that person exists, and see if any of these are actually ticked off. Or you may, if you don't know who's going to be using the space, if it's a speculative space, uh, and the tenant or the client is not yet known, you may have to make some decisions yourself as a designer as to which ones might apply, and then incorporate them as listed assumptions in your design. So you could be faced with those two scenarios. But if you start ticking off on table 1, if you tick just 1 to 2 conditions, then you have to raise the default illuminance from the application tables by 1 step on the scale of illuminance. And don't worry about that. You will see that shortly. You'll see what I'm talking about. And if it's 2 plus conditions from table 1 above, so it could be perhaps a jewelry workshop or an electronics workshop, and there are known to be people with low visual capacity or visual acuity problems, then you could raise it 2 steps on the scale of illuminance. Conversely, table 2 allows you to go backwards from the default specification. So if you can tick one of those or both of those, then you can actually go down a step. We don't think that's going to apply very often, if I'm honest, but I'm sure somebody will make it stick on a project at some point in the near future. When we talk about maintained illuminance, this is the illuminance value that we deliver at the end of the maintenance factor period. So when we get to the first service interval as dictated by doing a maintenance factor calculation, which we should all be doing and not just putting 0.8 in. Then if we do a proper maintenance factor calculation, it might tell us that after 70,000 hours, then the luminaires will need cleaning and possibly relamping. So the maintained illuminance is the illuminance you should be delivering on the day of that service due, that first service due. So that means that until you get to that point for several years, you may be actually overlighting the space for the value you want as the illumination depreciation finally glides down to that point where you get to the first service. So that is another subject again of overlighting to satisfy maintenance factors and the energy actually wasted in those intervening months or years. So let's look at an example. So before we start, there's the new table. Unfortunately, I haven't got an electronic pointer with this platform system, but table 44, for instance, educational premises, auditorium, lecture halls. I thought I'd pick this one, it should be quite relevant. The first two columns, starting left to right, pretty obvious. It's got a reference number, so you can find it again, task activity area. And then you've got your maintained illuminance or your lux level. So your required or your default in this case is 500 lux. And modified, if we have to start applying context modifiers, it could go up to 750 lux. Okay, so that's new. And then if we move to the center of the table, UO, that's uniformity, that's pretty much as it always was. And then RA or CRI 80, pretty much as it always was. And then there's this mysterious RUGL, which just means the upper limit of the UGR or discomfort glare factor that's recommended for this application. And you should see the familiar number of 19. And then we got these last three columns. The first one, EMZ, that is the cylindrical illuminance value, the minimum cylindrical illuminance value for this application. And then also you need to get a minimum lux level of light or illumination on both the walls and the ceilings as well to make sure the space is bright and doesn't have that dark sort of tunnely cave feeling about it, which psychologically does affect people who are trying to study in this space over any length of time. And then quite often there's a box with some specific requirements, so the lighting should be controllable, particularly you'd want lighting scenes, say from conventional teaching. If you then turn to AV and you need to drop the lights down a bit so people can see the screen, so there's the usual obvious notes in there. And then you'll see I brought table 1 over into this example. So we would have to consider some of those items on table 1 as part of our design once we opened up this table. So let's take an obvious one. The visual capacity of the worker is below normal. In this case, it could be the student. So as soon as we tick that one, we've got to raise the required illumination value from 500 lux by 1 step, which means it goes up to 750 lux, not 600 lux, but 750. Okay, and this is where the scale of illuminance comes in. So the reason the scale of illuminance is arranged the way it is, these are the steps in illumination levels where a human being can perceive a difference in change of light and find it beneficial. So if you were actually to say, well, do we really want to go from 500 lux to 750 lux? Maybe let's go somewhere in the middle, round about 625, as a compromise. The people using the space wouldn't actually benefit from that. It wouldn't really benefit their visual acuity at all. You'd have to go to 750, and again you'd be using more power than necessary without any obvious benefit. But let's just hold that thought. I mentioned power there, and obviously we have to think about low carbon solutions, and lighting is an interesting one because we can go very low energy with lighting, but quite often it's at the expense of the lighting quality. So we always have to find a balance in between. And what the standard doesn't tell you is that 500 lux is only actually required at the task area where people do work. And if you're moving up to 750 lux, if you had, say, a big open plan administration office with 50 people working in it, would you really want to light the whole office to 750 lux because 2 people have visual acuity problems? Probably not. So for 48 people, it would be overlit, and you would, a bit glary, so they would suffer perhaps a little bit in terms of productivity, and also you'd be using more energy than you needed to be. So you could end up on a sticky wicket with the sustainability engineer who's looking to decarbonize the project as far as possible, maybe even heading towards net zero carbon. So we have to strike. This is where we have to start applying lateral thinking thinking when we use this standard, because it doesn't tell us the entire story. It wasn't really written with net zero carbon in mind. Okay, so this is where we have to think about it and not just accept the numbers. So we're in a situation now where we've ticked one box from table one, and we've now got a 750 lux project on our hands. So it doesn't end there. So there's the modified requirements. You'll see at the top left-hand side, it's gone up to 750. And if we bring that down to the final requirements, it's also going to affect the last three columns as well. So you'll see that actually the cylindrical illuminance has gone up from 150 at the default 500 lux to 200. And also we've got to put more light on the walls and the ceiling than the default. So this whole thing starts to run away with itself in terms of lighting and also energy used. So in terms of lateral thinking, what I would recommend that you do is say, well, actually, there's only two people that we know about using this space that have got visual acuity problems. We will light the space to 500 lux, and where people put their hand up and say they can't see properly, we will put either a desk lamp or a freestanding luminaire next to their desk to give them that extra illumination that they require, so we're not seen to be discriminating against them. And in that way, you're targeting the light for the problem that's been identified just where it's needed and not everywhere at the expense of using more energy and overall lighting the space, and to the discomfort of the vast majority using the space. Now the standard doesn't tell you that, but that will still give you a compliant result. So just carrying on from that, table 44, here's some other areas. So if you follow the standard, lighting a lecture theatre perhaps is just going to become a little bit more complex than it was in the past. So these are all of the the sub areas surrounding that area. So your seating areas starts at 200, might go up to 300. If you've got any sort of teaching walls or good old green and white boards, 500. But you'll see in the specific requirements, you've got your vertical illuminance and reflections to be considered as well. Otherwise, you'll just get a big flash coming back off a whiteboard, for instance. Um, Demonstration tables in auditoriums and lecture halls, 750 lux, could go up to 1,000 lux. Light on the teacher and presenter, we talked about cylindrical illuminance there. And then light on a podium area. So yeah, if you're following the new standard, then yeah, all these things need to be considered. Okay, so let's move on to temporal lighting artifacts. Just do a time check. Okay, so temporal lighting artifacts, or TLAs, it's a collective term. There's three artifacts within that collective term: flicker, stroboscopic effects, and phantom arrays. We're only flicker and stroboscopic effects are represented in the new standard. Phantom arrays might come later, but at the moment it's really concerned with LED lighting in the automotive industry, which is why it doesn't appear in this standard. But flicker has been given a metric. It's basically flicker is caused by usually by a modulated signal coming out of an LED driver to the LED array. So it's a time modulated signal, and it's been given a value at international level, and that value or metric, when it's measured in a laboratory, needs to be 1 or less on the PLM over ST scale. And then stroboscopic effects, which might occur, say, if you've got, say, a laboratory or a workshop with rotating or reciprocating equipment or machinery, which could be a health and safety hazard, then that needs to be at a metric of 0.4 or less. And again, that can be measured in a laboratory. And we'll talk a little bit about that, how these, why these phenomena occur, and where you can find out the information when you're building a luminaire schedule to make sure you're not inadvertently introducing luminaires that will produce unacceptable levels of flicker or stroboscopic effects into your project, because it will be very expensive to fix afterwards, unfortunately, if people start to complain. So basically, this has been a long time coming. If I just give you some background, there was, quite often people would say there was a flicker problem back in the days of fluorescent lighting, and there was, with a very simple choke or ballast. You could get a flicker problem, which became apparent after a few hours in that space and caused people to get tired eyes and maybe even headaches. So A few years ago, when we were still using fluorescent lighting, the high frequency ballast was developed, and that solved that problem. And that's great. And then LED lighting came along, and the problem started to reappear again with certain LED luminaires. And people said, well, you solved this problem with fluorescent and you introduced HF ballasts. How hard can it be? Well, actually, it's not that simple. A HF ballast had a 230 volts AC mains input and also gave 230 volts AC output usually. So it was AC in, AC out at more or less the same voltage. So the engineering required in the ballast to solve the problem and the high frequency conversion was very different to the engineering that you would need to apply to an LED driver. So we had to start again, and also because we are now in a sort of a globalized trading environment as well, we had to get international agreement on the test method and the metrics, which took a few years to come together. And finally came out of two IEC, that's International Electrotechnical Commission technical reports, one in 2018 for stroboscopic effects and one in 2020 for flicker. So once we had that international agreement, two things happened. Those metrics went into Eco Design 2021, which is European and UK legislation for the manufacturers of light fittings, if you like, or luminaires, in terms of energy efficiency and also technical performance. So they are legislated for within eco design. Um, and then also when this standard was released last year, around about September 2021 as well, exactly the same metrics have gone into this standard. So it's covered both in a standard and within luminaire manufacturing legislation as well. So it's important really to look at a luminaire at the specification stage and say, well, what are the flicker properties? If somebody tells you they're offering you a luminaire that is flicker free, um, treat that very, very carefully. There is, in my opinion, no such thing as a flicker free luminaire. Only luminaires that have either got a flicker problem or luminaires where the flicker potential has been reduced to acceptable limits. So probably the only LED products you're going to find that can be claimed to be flicker free are a battery torch or an emergency light after the mains has gone off with an LED light source in it. So be very careful with that one and the claims that are made. Um, Stroboscopic effects, again, this has been around for years, this problem with lighting. So back in the day, again, going back to fluorescent lightings, if say we had a workshop full of rotating and reciprocating machinery, um, if you had a stroboscopic effect, it could cause, say, the chuck on a lathe to appear to be spinning or even stationary, when in fact it was turning at several hundred or even a few thousand RPM, which is an obvious health and safety risk if somebody reaches out to that chuck thinking it's stationary. Um, but what we used to do, where we had rows of fluorescent lighting, we'd put them on alternative electrical phases, and that usually solved the problem. But again, you can't do that with LED lighting because the driver is a precision DC power supply with a low voltage, usually DC output. So again, it required a different approach within the driver. So usually flicker and stroboscopic effects are engineered out within the luminaire's driver. Um, Sometimes you can get flicker introduced by noise on the mains wiring feeding the luminaires. There may be other things within the building or on the site, such as substation switching in and out, or big motors that start up every now and again that are putting noise onto the electrical wiring in general. If this enters a luminaire, the driver should be able to withstand and suppress a certain amount of noise. That's part of its CE or UKCA test mark. There is a test, if you like, for electromagnetic compatibility and immunity, but only to a certain value. So usually the driver will dampen that effect if you've got external noise coming in, but on the odd occasion, the noise might be above the threshold that the driver had to be designed to, and it may go straight through the driver and cause a flicker problem at certain times of the day. It's very unusual. I've only seen it once in 10 years, but it can happen in rare circumstances. So how do we get to making sure that we're specifying luminaires with acceptable flicker and SVM characteristics? So there's an LED driver data sheet. So at the moment, because this is quite a new subject, it only appeared a few months ago, 6 months ago now, you probably won't see the information on a luminaire data sheet in a not any obvious position, you're probably going to have to ask the manufacturer or the distributor to confirm that the luminaire does, have compliant flicker and stroboscopic effects values attached to it. And the way to evidence this is to look at the LED driver data sheet. So you'll see here the technical data for a typical driver, and I've put a red box around the two metrics we're talking about in this presentation, and you can see they're presented and the values are where they need to be. So we know that this luminaire, to all intents and purposes, will be compliant by checking the characteristics of the driver. If you're looking at a driver data sheet and those characteristics are not present or nobody wants to give them to you, the chances are you're specifying a luminaire that's going to cause a flicker or a stroboscopic problem or both into your project, and it could be quite an expensive fix. Just to give you an idea what should be happening in terms of flicker, and people do say to me, but you can check a luminaire by putting your mobile phone into camera mode and looking at with the camera in real time, and you'll see the flicker on the screen. Um, to be honest, that is another urban myth. Yes, what will happen is that the light source will confuse your camera as the CCD chip tries to make sense of what it's looking at, and you probably get some black lines rolling across the screen, which you might think is flicker. Actually, they're not. It's just the phone getting confused. And if you had a single luminaire and walked around it with your phone, the frequency of roll of those black lines would change, which is a little bit unusual because if something's flickering, it's flickering. The flicker value or frequency doesn't change as you walk around it with a phone. So yeah, don't think by getting your mobile phone out when you're looking at luminaires that that's going to give you anything reliable, because it won't. It has to be done proactively. If you're doing it proactively, this is how it should be done. So that little photograph there on the right hand side, that's a customized luminaire that we built for a customer up at Thorn Lighting in Spennymoor, and the customer had flicker problems before and had been caught out and wanted to see a certificate for each of these custom luminaires. So there's one of the custom luminaires in the lab being tested. So that little black box on the cardboard box has got a photodiode in it, and then there's a little snorkel on the front, so it's picking up the light just from the luminaire, and then it's going into some software which evaluates it for flicker and stroboscopic values. And we're also monitoring the mains as well with the oscilloscope for any noise coming in from outside that we may need to take into account. So this is really the way to do it. It should be done through careful engineering design of the driver, and also the luminaire can be tested, or if you look at the driver data sheet, you're 99% certain that you're where you need to be with your specification. Okay, so the next new one that's come into the standard, but is not new, it's been around since 2007, is the lighting energy numerical indicator. So when we talk about lighting energy, most people will do a plot, and again, we'll use this Dialux plot as an example on the right-hand side of the screen, and that their eyes will go straight to the bottom line, and it will give you a specific connected load, in this case 3.69 watts per square meter. Okay, and people say that's it, and they get transfixed with that number, and somebody might say this job has to be 5 watts per square meter or less, but that number is slightly misleading, because that's the worst case electrical load. That's everything switched on at 100% output, and it may be Dali lighting, for instance, it may be dim during operation, not using as much power. So that's your worst case. Useful for calculating your lighting circuits and getting your cable sizes and your volt drops correct, and your circuit breaker specified correctly. But that's about as far as it goes. And you can get hung up on that number, especially if somebody's given you a target number like 5 or 4 watts per square meter, because your only option then will be to try modeling different luminaires to hit that magic number at the bottom. And along the way, you'll probably wreck your illumination and your uniformity and your UGR. So you'll solve one problem and create another one, and you could spend several days on it doing this and get quite frustrated. But there is an easier way. So if you go to Part L of the building regulations, then it does tell you there are thresholds for lighting energy in use, but it uses the Lenny method, what we call the simple version of the Lenny method. And what this does, it takes you through a series of scenarios. So if we take the number from Dialux, the 3.69 watts per square meter, we can actually convert it into kilowatt hours per square meter. We know what we're lighting to, in this case 500 lux, and then we need to ask ourselves, how is this space going to be used in terms of lights on? So in this case, we've said 9.5 hours for 5 days a week, call it 48 hours times 52 weeks of the year, 2,500 hours per annum. So from that, we can work out the kilowatt hours per square meter per annum. Okay, and if we look in Part L of the building regulations, and I'm using the English building regulations because these are the most recently updated building regulations for the United Kingdom and therefore the most punitive. Um, the limit for a job that operates its lighting for 2,500 hours a year at 500 lux is 12.23 kilowatt hours per square meter per annum. Okay, so we want to get a minimum of Part L compliance because that's what we should do as responsible engineers. And in fact, the employer's requirements may want to future proof and go beyond that. So it may be down at about 10 um, kilowatt hours per square meter per annum, just anticipating the next few years, and also to save energy, which is a good thing, without destroying lighting quality along the way. But how does Lenny work? Well, I'm not going to give you a lesson in Lenny. But it's basically a four-step calculation which takes into account your daytime lighting energy. We know that from Dialux. Any nighttime energy that might be used, we will know that from how the space is going to be used, and then any standing load. So if you've got things like Dali luminaires and emergency lighting, battery chargers in luminaires, and some lighting control devices, they all take a small standing load. So even if you switch the lighting off on a Dali system with a digital signal, which basically just switches the output of the driver off but leaves the driver powered up so it can communicate, even if you think the lighting's off, your lighting circuit is still drawing a small amount of power or a standing load. So we have to take that into account because on a big project that can mount up to several kilowatt hours. And then also there are derating factors you can apply for use of automatic lighting controls. So without going into doing this calculation, and there is a worked example, by the way, in the latest version of Part L of the building regulations for England. Let's see what happens on this particular project. So if we look at this table below, if we take the information we took from Dialux, which is just purely what the luminaires are drawing at full power, doesn't take into account the effects of emergency lighting chargers, Dali drivers, or the benefits of automatic lighting controls. The cost in that space are nominal, and I know it's a little bit farcical today, 10p per kilowatt hour. To burn those lights in that 2,000 square meter space on the last slide would cost about £2,375 a year in energy. If we use the Lenny method and we took into account how we use the space and the benefits of the automatic lighting controls, and took a more real world calculation prediction, then actually you would see a reduction of about 23%. Or £1,832 a year for the same lighting installation. And if you convert it back into watts per square meter, you've got 2.8 watts per square meter, which is more realistic than just taking the worst case output. So if your if you're doing modeling and your plot is not quite where you want it to be, you might be beating yourself up looking for a different luminaire or a different layout, which may take you several days to solve. If you do a Lenny calculation for the same job, you might find you're already where you need to be. You may be at that target that's been set. You're just using a bit of a blunt instrument to try and illustrate it in a technical submission. So you should do a Lenny calculation really to comply with the building regulations. Yes, you can look at luminaire efficacies, but this is probably a more granular way of doing it. And as we go into a sort of a low carbon, net zero carbon future, then I suspect that although this method has been around since 2007, it's going to become your friend even more and more to get those numbers right. Um, we did do a case study in Zumtober Group when we knew this new standard was coming. We created a virtual model of, in this case, a lecture theatre. So we got 4 benches and usual array of symmetrical ceiling lights to satisfy the designer or the architect. So it's a 400 square meter space. And what we wanted to do was test all of our luminaires in the space in a typical popular configuration that might be required by a client, and also in some cases look at the melanopic content of some of the suitable luminaires for a lecture theatre or an office space for melanopic content for well-to specified projects. So we tested about 30 luminaires and probably did about 5 tests per luminaire in slightly different configurations in the same model. So they were all tested to the same standard, just to see what would happen as this new standard came to fruition. And we did draw some conclusions. So one of the conclusions that we drew was that you need to use targeted illumination. Just because the standard says 500 lux doesn't mean that we're going to light this entire space to 500 lux. That is that area represented ostensively in green. That would just be silly, because that would be overlighting in most cases, and also using a lot of unnecessary energy, which doesn't support the drive to decarbonisation. So we need to think now about complying with the standard, but just targeting the 500 lux where it's actually needed, which is the workstations where people do a job of work. The green area is actually a notional circulation zone where people just move around. And outside, we've got a corridor, which again only requires 100 lux according to the new standard. So what we've got here in this green area is, say, well, okay, the luminaires on the ceiling, if we had we should have a lighting control system in this day and age. What we'll do is we design the whole space to 500 lux, but when we walk in a room, we create 2 lighting scenes with a lighting control system. So the lights will switch on automatically, but the lights over the workstation will switch on via lighting scene 1, say, to the full design output of 500 lux. But the luminaires over the green area, where we only need a 300 lux, will respond to lighting scene 2 and only operate at, say, 70% output to give us 300 lux. So this can be set up and calibrated as part of commissioning. So what's happening here is you're only actually delivering the higher lighting level to where it's really needed. And then the other area, if you go back to the application tables, a circulation zone or areas immediate to a workstation specified at 500 lux can be lit at 300 lux. And also we've got a photocopier in the corner, and a photocopying station as well only needs to be lit to 300 lux. So we're using the lighting where we need to be, and we're saving some energy as well. Now, why did we make the decision to use 500 lux and 300 lux? Well, it comes back to this scale of illumination. So you can see there we've got 500 lux. The next one down is 300 lux. And this means that people will be able to make a visual perception between the workstation and the notional circulation zone. And it should be quite pleasant on the eye, as well as saving you energy. You could take it down to 200 lux if you want to, but then you start to get much more marked contrast, and some people might not like that. So again, you could set the second lighting scene to 200 lux and try it out at commissioning if you've got the luxury of time, see how you get on with it. And if you don't like it, you could move it back up to 300 lux, or even set 3 scenes. So it's just a simple matter of selecting the ones that were preset and then locking them off. So it can only be that. Again, if you don't know who's going to be wanting to use the space, you might say, but there might be some people who got visual acuity problems here. So maybe we need 750 lux. Well, in that case, you design the whole space to 750 lux, and then you would probably turn the lighting on over the workstations initially, or for handover, to 500 lux. So that would be your first lighting scene, and then your 300 lux would be your second lighting scene. And if the client phoned you up, say, in a year's time and said, we have some people now using the space that have visual acuity problems, we need a higher lighting level for them, you could either introduce a table lamp or a freestander at that workstation for the affected people, or you could just send a third lighting scene to, say, 3 or 4 luminaires over one workbench, and turn them to 100% at the 750 lux you built in reserve. You certainly wouldn't leave it at 750 lux at handover, not knowing who was going to use the space, but it's nice to have that reserve built into your design if you feel that's the right thing to do. Rather than having to tell the client when they phone up and say we need more lighting because we've got some new people joining, and saying, well, we're going to have to change all your luminaires to facilitate that. So it's, that's just thinking ahead, perhaps a little bit of due diligence. So in summary, then, we need if there's three things we need to think about from this presentation, is that the quality of light is actually a function of time. So this is when it comes down to selecting luminaires. The brightest, sparkliest luminaire is not always the best. If one looks a little bit dull and muted, but it's still, you're told it's still got the same lumen output, then the chances are it's a low glare luminaire and it's the one for you. So you do need to ask questions when you're asked to make decisions about choosing luminaires, about the low glare properties and the low flicker properties of luminaires, because those two items alone, glare and flicker, are going to destroy a space for the users that have to use it over any length of time in terms of their productivity and morale, as opposed to the person spending just a few minutes deciding in a meeting which luminaire they want to carry forward onto the project. So think about that one, please. Context modifiers. People will have various views on modifiers who've just had a quick peruse of this new standard and say that waste paper bin in the corner might have to be lit to 750 lux according to the new standard. I hope you can see that's not necessarily the case, that you can apply some lateral thinking here as a professional engineer and just target those higher illumination levels where they're needed, and then there is a scale of illuminance to allow you to accurately work out what light can be in the peripheral areas, without causing too much of a contrast and creating some raised eyebrows when the space is occupied. And then again, as we're all, facing the challenge of decarbonising our designs, but preserving, in this case, the lighting quality, think about using Lenny to look at your energy prediction calculations rather than just the watts per square meter statements on the bottom of lighting plots. You may find, as I say, you're wasting a lot of time looking, to modify the design to get that magic watts per square meter down to where the sustainability or the employer's requirements people have told you they want it to be. And the same job with the Lenny calculation, in that case, took 23% off, and that within a couple of hours that might take me to where I wanted to be anyway. So that's the end of the presentation.